just wanted to like understand your take. Like, what do you think are like the bigger problems worth solving over like, let's say, the next 5 years that are really sort of critical to making RL work in the real world? Like,
yes, it's an excellent question. That will be the first thing we'll do in today's lecture. Challenges in real world decision making. So hopefully some of those questions might be addressed. If not, we'll have some time for discussion. So I think it's a very timely point that you brought up, Ayush. So we'll start with that. Then we will look a bit about non-stationarity and decision making. We'll wrap up inverse RL with Gale. Then we'll discuss some open questions and hopefully a bit of multi-agent stuff also with these questions. So let's get started. So what are the challenges in applying reinforcement learning, or generally speaking, doing decision making in the real world? Right. So the first thing is reward design and measurement. It's something we discussed, and we looked at how we can leverage reward shaping or inverse RL to partially overcome this issue. Right. The other thing we looked at, or another problem that we considered in the class, was about safe exploration. Right. And some methods that we discussed over here were offline RL, learning from demonstrations, and the last lecture we discussed about safe RL. Then another big issue with a lot of learning techniques, whether it be model free or model based, is data efficiency. And some things we looked at was, again, using demonstrations, intrinsic rewards, sim to real, and in some cases model based methods could be much more efficient than model free methods. And one question we did not look in this class is, how do we trust systems which are deployed in the real world? Now, there is research ongoing which is trying to provide performance certificates to systems. Just like when an airplane is flying, someone validates that the failure rate of airplanes is going to be very, very small. So similarly, could we provide some kind of a certificate saying that, this system will work, is either guaranteed to work, or some kind of a probabilistic certificate which says that in more than 99% of the cases, the system is not going to fail. Something which is an active area of research. The other challenge in real world is of non-stationary dynamics. But this could happen due to many reasons. Right? For example, there are new events like COVID happened. It changed many things. Some things are cyclical. For example, if you consider stock markets, sometimes, near festivals, they might have a certain trend, or if there's a quarterly report period, it's likely the stock market will either go up or go down. So there are some trends which end up being cyclical in nature. So we'll take some time to look at non-stationary dynamics. I'm not going to spend too much time over here. And another problem is of long horizon tasks. Right? So a lot of methods that we saw in reinforcement learning were not really solving long problems. They were solving problems which were maybe 100 steps or 200 steps long. So we did look at some methods. We looked at action primitives. We look at some hierarchical approaches to address these long horizon tasks. And finally, one major issue is sensitivity to hyperparameters. I think a lot of you had issues in your homeworks because of trying to tune these hyperparameters. And the other is just performance variance. Even if you use exactly the same hyperparameters, but end up using different seeds. So all the problems on these slides is not necessarily specific to reinforcement learning. They are going to apply generally to any decision-making algorithm, whether it be reinforcement learning, whether it be imitation learning, whether it be some classical control technique. So if we want to, maybe focus more specifically on reinforcement learning, there are some issues which are maybe more specific to it. For example, credit assignment, right? Which we looked at a couple of ways to overcome it. One of them being discounting, one of them, again, having a hierarchy. One open question right now, which people are pursuing, is can we learn to assign credit? So if you think about the discount factor, it's a heuristic, which we use today to assign credit. But we don't have to stick with that heuristic. Then the other way we discussed about credit assignment is through curriculum learning. And maybe if we are doing simpler tasks, we learn a reasonable policy. And because the task is simpler, maybe assigning credit is also simpler, so that once we go to a harder task where credit assignment will become much tougher, our algorithms can still work. Then in the initial part of the class, we spent a lot of time talking about the bias variance trade-off and how we try to improve the performance specifically of on-policy algorithms by performing this trade-off. Right? So we looked at how we can estimate the returns by either using a critic or by doing Monte Carlo rollouts. And in that context, we discussed generalized advantage estimation. Then, coming back to the problem of data efficiency, it's worth noting that the dominant reinforcement learning paradigm is based on utility theory. And utility theory comes from economics. And what it says is, we should maximize average reward. But nowhere in utility theory do people talk about that the data which we are using to estimate utility is finite. So it is insensitive to that particular fact or that real world constraint. So we don't necessarily have to base decision making on utility theory. There are other choices. For example, one alternative is case-based decision theory, which was specifically designed for low data regimes. There's an excellent review article by Sam Gershman, which compares thinking about reinforcement learning from a utility theory perspective against a case-based perspective. So I think one caveat is, we have implicitly assumed utility theory throughout the course, but that is something which is not necessary. It's an assumption that we had made that we need to, estimate the value function and the Q function. Right? We could have decision-making algorithms which do not explicitly estimate those quantities, yet take decisions. So if you're interested in an alternate view, I highly recommend going through this particular paper. It's also an excellent read if you want to know about different kinds of memory in animals and humans and how memory and learning interact with each other. So highly recommend it. Then what have people done in reinforcement learning typically to account for finite data constraints or make it more sample efficient, or to improve the performance is to improve the optimization method. Right? For example, we looked at natural gradients, how we can go from simple reinforce to PPO, which is applying constraints such as the policy should not change too much so that we can find a good solution. Then how do we correct for biases? For example, Q function is often overestimated. We looked at how double Q learning could be used to improve performance. Then also when we're looking at actor-critic algorithms, such as DDPG or SSC, what we found was that updating the critic more often than the actor is helpful. Right? So those are some of tricks or methods that we have been able to develop to improve our optimization. But there is a lot more to be done. The variance of our estimates are still high, and issues like overestimation still exist. So if you are more mathematically inclined or you're interested in optimization, many things you can approach from that perspective. So, and then the other thing which is not here on the slides is offline RL, right? There's a big gap between what we can do with online data sets and what we can do with offline data sets. So we'll talk about, so I mean, hopefully this kind of gives, maybe like a cheat sheet or a bullet list of some of the problems which are present in decision making in the real world, and maybe some problems which are specific to reinforcement learning, and some methods that we have discussed to address these problems. So let's pick up one thing that we have not discussed previously in the class, which is non-stationarity. Now, it turns out there is no, one method that fits all kinds of non-stationarity. There are different kinds of non-stationarity and different kinds of methods can be leveraged. For example, one non-stationarity is recurring events. For example, we know at 9 a.m. in the morning, traffic is high. Again, at 5 p.m., traffic is going to be high. Right? So if I'm planning routing algorithms to, say, for Uber or for Lyft, it's something worth knowing. Right? Similarly, in stock markets. Then there is a problem of drift. For example, my sensor could be noisy, so things are changing over time. Or if I'm developing algorithms for trading, we know that most indices end up increasing in value. So there's a drift which is happening in those indices. Then the environment might appear non-stationary because we can only observe a small subset of the environment. So this could be because our sensing is limited. Right? For example, as a human, we cannot observe everything. We can only observe things which are in front of our eyes. Or, the agent might have some kind of memory constraints so it cannot accumulate information over time. Then another kind of non-stationarity is caused in competitive setups. For example, security. There's a virus and there's an antivirus, right? Or there is, I guess virus applies to a couple of things, virus such as, what is in computer programs, but also, like we have COVID and we are building vaccines, but then the new strains which come up. So there is, this nature where the environment is changing because of interaction between two separate entities, which causes non-stationarity. And then there are new events. For example, a war happened, a recession happened. This is going to change the dynamics of how things might evolve. So, roughly or broadly speaking, we can group non-stationarity into these buckets. And now let's look at, some methods which one could leverage in each of these buckets. Before that, let me see a question in the chat. Oh, is this a comment? Okay, perfect. Thanks, Juma, for putting that article in the chat. Then, okay, so let's look at the recurring event example. It's a nice quote by Mark Twain. It says, October is one of the peculiarly dangerous months to speculate stocks in. Others are July, January, September, so on and so forth. So if you look at trading, there are some recurring events. For example, there's an upward bias at the end of the month. There's a bias when holidays are there. There's a bias when quarterly reports are going to be released. There's a bias when there is, some particular market committee meetings which end up happening and they make some announcements. And the question is, how do we address this problem with recurring events? So one possibility is to augment the state space to indicate such events. Now, what do I mean? So concretely, taking an example from trading. So what I'm describing is the state space based on this article whose link is on the bottom. So, they have some state features which are relevant. For example, the close values from past 3 days, and some other indicators of the value of that asset, but they also indicate, is it the end of the month? Is it a holiday? Is it one of those events? Is it one of those special times that my agent should be aware of? And that is something which I can make it part of my state. Now, on the face value, this seems like a good idea, right? So should one augment the state with such indicator variables, right? So, we have a small poll about augmenting the state space. So let's, look at this poll, read through it. So this is a multiple choice one. And the options are asking you to judge whether state augmentation will make the problem stationary, and if state augmentation will lead to higher reward, but with more data or with less data. So we give some time to think about it. Maybe let's say 30 seconds, and in 30 seconds, let's try to answer this. So last 5 seconds, if you're on the fence, I suggest, make your call. We have only 7. Okay, we're closing in to all people. So I think there are 3 more people whose vote we are waiting. Okay, final count, 3, 2, 1. Let's close the poll. Let's see what people thought. So the first thing was the agent might receive higher reward, but require more data. And 7 of you agree with that, which is the most popular option. And the next popular option, with the augmented state, the problem is still non-stationary. So first, let me comment on the first one. The agent might receive higher reward, but require more data. Why would it require more data? Does anyone want to comment on that? Just speak it out or maybe type in the chat. No? Well, if we augment the state space is going to become larger, right? So if we have a larger state space, which means I have a higher dimensionality of my problem, classical machine learning tells me that I might require more data to fit it, right? So non-stationarity can help us achieve higher reward, but at the cost of potentially requiring more data. Then the second question is, with the augmented state space, is the problem stationary or non-stationary? Yeah, so another perspective, brought by Anubhav is that, an event such as turn of the month is only going to happen, less often than I can get the values of stock. So because it's happening less often, I might have to wait for longer to get enough data so I can make use of that particular signal. That's a good point also. Now coming to the problem of stationarity and non-stationarity. But I think if you are able to identify the correct set of augmentations, your problem will become non-stationary. But consider the fact, there were 3 rooms. In one room, the gravity is 9.8. In other, it is 0. In other room, it is minus 9.8. Right? So there are 3 rooms with 3 conditions. Now, if I knew which room I am in, then the problem is completely stationary because the dynamics are not going to change. If I throw the object, I know how it is going to either come down, just be where it is if gravity is 0, or go up. Right? So essentially, by augmentation, I'm clustering my state space into distinct parts, where in each part of the state space, the dynamics could be different, and the augmented features help us identify what dynamics is operating in that state space. So I would say, if we augment it with the right variables, the problem would become stationary. Any comments or questions on that? No. So practically speaking, there's a trade-off between data and the rewards we're going to get. So, what do people typically do? I mean, they try both versions, with and without, and use hypothesis testing, or a fancier way of saying a hyperparameter sweep to figure out which model to use. But that's something to keep in mind. If you have recurring events, think about augmenting the state space to provide that information. So we discussed this part. Now to address drift. So there are a couple of things one can do. One can try to normalize the observations to remove the mean or to remove the drift, which is called as detrending. It's a whole field in itself. Then, there are standard techniques like data augmentation, domain randomization, robust optimization that you can leverage. Then, what about the scenario of partially observed environments? The problem over here is the sensing is limited, or I might not have sufficient memory. So if I can accumulate information over time, that might help resolve the problem. Or maybe I can infer the latent state. What do I mean by inferring the latent state? Instead of doing state augmentation manually, maybe I can automatically infer what part of the environment I am in, or automatically cluster the environment into groups which have maybe different dynamics. Right? So that is, one other possibility. Another is fast adaptation. And I can quickly adapt to new things which are happening, which is also a standard way to deal with, very new events. Right? So in fast adaptation, we discussed briefly about meta learning. Again, robust optimizations, domain randomization are some things which improve adaptation. So, hopefully, so this was a very brief overview of non-stationarity and how to deal with it. But I hope, if you now see a problem, you can maybe categorize it into one of these parts, and then, at least have some pointers to start looking in. So that's all I'm going to say about non-stationarity. If there are any questions, now is a good time to bring them. Nope, I don't see any more questions. So, okay, so let's close the non-stationarity part. And let's switch gears and wrap up one loose end, which we never wrapped up, which was in context of inverse reinforcement learning. So we talked about inverse reinforcement learning, but mostly in tabular setups. We did not talk about how to scale it up to non-tabular setups. So I'll briefly give the intuition behind, one popular IRL or, style algorithm, which is Gale. And so Gale draws its inspiration from some of the fundamentals that we built in inverse RL with the techniques to generate data, which is specifically generative adversarial networks. So let me first briefly talk about GANs and then show how GANs help us scale IRL to high dimensional state spaces. So what's the main intuition behind GANs or generative adversarial networks? So my goal is that I want to generate some data, right? So suppose I want to generate fake currency notes. So I am the generator who is the counterfeiter, and this is very easy for the discriminator to detect that this is fake. Now, I might get some signal about the fact that this is fake, so I might then try to change it. Right? So maybe I picked up on the shape as the feature, then shape. And I think, maybe I can fool the discriminator now to believe that these two nodes are the same. But over here, the color is off. So, maybe then what I can do is to get some signal which says change some other feature, and I can produce this other node. But now these nodes start looking similar, so it becomes hard for the discriminator to detect whether the data generated by the generator is true data or fake data. So what we have done is essentially, set up a game where is producing data, and the discriminator is trying to say whether this data is true or fake. Right? And empirically, it has been shown that this two-player game ends up generating really good things, or it ends up modeling the data distribution. So mathematically, how do we set it up? So it's a two-player min-max optimization, where D over here is a discriminator, right? And what we are sampling is, so P of data means the data set that I have. So I have some, say, sample of images, and what I'm trying to do is to say samples is high, and the probability of samples which are being generated by the generator are low. So generator is a network which takes in noise as input, which is Z, and outputs, say, an image. Discriminator takes the image as input and tries to classify or tries to Sorry, it seems like my Wi-Fi went off, but now I should be fine. So maybe I dropped off when I was explaining gyans, but I'm also hoping most of you have seen gyans before. So if someone has a question on gyans, please raise it now, or otherwise I might, just, breeze past it in the hope that most of you or all of you understand by this time what gyans are. And, just to remind, the kind of images that you can generate with gyans are as following, which look pretty realistic, showing that. So why do these look realistic? Initially when you generate images, they're just white noise, and the discriminator can very easily distinguish between natural images and noise. But as the generator improves, because it is trying to fool the discriminator, it ends up producing better and better images. Right? So at this point, the discriminator is getting fooled. Or even these faces are all fake faces which have been generated. Okay, so what's the relationship between generating faces and images and inverse reinforcement learning? So recall apprenticeship learning that we discussed. Right? So we had this setup where we have a reward function which is unknown, and the reward function is a linear combination of the state features where W star is the optimal reward function, or the W star is the parameters for the optimal reward function. And what we saw was that if we look at the value function, right, then we can rewrite the reward as W times the state features. We can bring W out, and what we have is just feature expectation. And what we saw in the previous lectures was that if I have the expert feature expectation and if I have the feature expectation of my policy, we can get a good policy by just matching the feature expectations. That is, I just need to do feature matching to find good policies. So this is exactly where gyans enter the picture. So what I can do is to say, let me generate actions in a state space through a generator which takes state as input and action as output, so that that state action pair is indistinguishable from the expert state action pairs. And so now I have my data of the expert, which is a bunch of state action pairs, treated similarly to a set of images, which we might get when training gyans on images. Then in both the cases, we have generators. In the image generation case, the generator tries to predict images, and we compare whether this image looks like a real image or not. In our setup, we'll try to predict the action given the state, and then look at the state comma action pair, and the discriminator would try to predict whether the state comma action pair might have come from the expert or not. So this is a way of doing feature matching. Okay. So we can write this mathematically, where the difference in the feature expectations could be written in this generative adversarial framework. So if the discriminator is fooled, it means that the expert and the policy distributions are matching. So this is pretty much the main idea behind generative adversarial imitation learning. It's pretty much taking two ideas and putting them together. One idea that good policies are ones which match the expert distribution, but the hard problem is how do we match expert distributions in high dimensional state spaces? We take generative adversarial networks and we put those two ideas together. So essentially, we end up optimizing this loss function, and there's an additional entropy term for exploration. Now we can go and compare results of this algorithm, which is shown in blue. So again, so the x-axis is the number of demonstrations which are provided on these different games. The y-axis is the performance. Now in orange, we have behavior cloning, and in blue, we have Gale. And so what you can see is that Gale ends up outperforming behavior cloning on almost all of these environments, which is consistent with what we discussed previously, that when inverse reinforcement learning works, it ends up being better than simply doing behavior cloning. Any questions on Gale? I see something pop up on the chat. Yes, Ayush, give me a couple of slides and I will come to that particular question. Any other questions? No? Okay, then let's march ahead. And now what we're going to discuss is some open research question, some perspectives, and we'll also cover a bit of multi-agent, with these perspectives. So I think some of the big research questions which are quite open. I think the first one is the reward design. And so I think eventually, instead of tuning all these hyperparameters of reward designs or all these coefficients, what we actually would like to do is to specify rewards via language. Some mechanism which is very intuitive for humans. The problem right now is machines understand one language, which is a language of numbers. Now, for humans, it's very hard to describe tasks in numbers. What we are good is at language, but machines are really bad at doing it. And this pretty much connects more generally to the problem of how do we communicate human preferences, or what the human wants the machine to do. And we spent an entire lecture talking about why or specifying tasks is a big problem, and what are some potential ways of trying to address it. So this problem of communicating human preferences is also linked with inferring human preferences, right? And if we can infer human preferences or human intent, one can also build agents which collaborate with humans. Right? So in some ways, you might think that reward design has got nothing to do maybe with human-robot interaction, but I think at a more fundamental level, they are very related. Because in both of them, the hard problem is for the machine to understand what the human is trying to do. In one case, it must just solve the task on its own. In the other case, it has to collaborate with the human to solve the task. So I think this research area of how do we communicate human preferences, instead of maybe spending all of our time on writing better algorithms, maybe we should think a lot more about how are we going to tell machines what we need to, or what the machines should be doing. Another wide open area is of observational learning. I mean, one thing that we would really like our machines is to have human-like world knowledge. And the question is, how do we put that knowledge into machines? Like classically, people tried building databases where they would put more and more content, but those databases end up being brittle, and it's very hard to put all the knowledge in form of rules. Right? This might remind you of lecture 1, where we use self-driving car as an example. And when it's very hard to specify rules which would let a car drive in all scenarios. One way, we as humans learn is by observing the environment around us. But machines have a challenging time due to several issues that we discussed. Right? One of them actually being related to the first point on this slide, which is inferring the intent of the agent whose video I am observing, and other problems like changes in viewpoint or the correspondence problem between the robot's manipulator and the agent or the expert which is performing the task. So observational learning, has not played a significant role in reinforcement learning until now, but it could be a significant part of how we could either pre-initialize our networks, or if the agent wants to explore, it could guide its exploration by observing, how to do a task. Right? Something we have discussed in the course, but something I'm trying to emphasize once again. Then the third thing is transfer learning. So, I think, so if you look at the problem of data efficiency, one approach is to say, let us build better reinforcement learning algorithms. Other approaches, can we come up with, better kind of curriculums or exploration algorithms? But, maybe a more fundamental way of overcoming sample inefficiency is to actually be able to transfer from one task to another. In supervised learning, transfer learning has been quite successful. And we can train on ImageNet, even go to CAT scans, we can go to MRI data, we can go to satellite data, and those models transfer. In reinforcement learning, for instance, we cannot transfer between two games, which might be very related to each other. So transfer is a big challenge in reinforcement learning. The other challenge, which is how will we trust these deployed systems? So when we recall the lecture which Kathy was giving on Tuesday, so she talked about these examples of using RL with Facebook messages which pop up on your phones. Now that is something with the cost of making a mistake is really low. Or for example, news article recommendations. So right now we have been able to deploy reinforcement learning system with, the cost of making a mistake is really small. But how would we actually deploy systems with the cost of a mistake is really big, or how would we trust those systems is a wide open area. Then, offline RL. I think maybe the first 5 years of reinforcement learning were about online RL, but a lot of practical problems, we just cannot collect more data, or the cost of collecting data is very significant. Or we have very good reason not to throw all the data, right? For example, if I'm trying to optimize advertisements I want to show, if I'm Google, I don't want to throw all the data I have in the past. I want to leverage it. So I think it's very possible that we'll see a lot more work happening in offline RL in the future. Any questions on these bullet points or these comments?
Can I sort of stress a little bit more on like what you were mentioning about observational learning?
So what I mean by observational learning is, there is a lot of knowledge available on YouTube, for example. right? So for an RL agent, instead of exploring randomly, could it maybe find, I mean, if I give it a collection of YouTube videos which say this is how the task should be done, and then I have a reward function which is very sparse. Why sparse? Because it is easy to define a sparse reward. Then could it leverage, those videos to efficiently solve the task that I gave it? Right. So instead of me, demonstrating to the robot by moving the robot, right? So what is learning from demonstration? Where I give both states and actions of how to do the task. Observational learning is where I just give a sequence of states without the actions. Something we do on a regular basis when watching video. Okay, so the next discussion I would like to have is about this question of the science of intelligence versus engineering intelligent behavior. So I think many times when you will read papers or think about research, I think it's important to distinguish between them. And so I think the purpose of maybe the first one, the science of intelligence, is to figure out what leads to emergence of intelligence, of how we can build intelligent systems, but they are not necessarily tied to a specific task, right? Versus engineering intelligent behavior might be, I have some tasks in mind, and how can I improve the efficacy of my current system, maybe by leveraging learning techniques. So to make these points clear, let us consider some examples of what would be questions which could be thought of as science of intelligence. Then you would look at some questions which could be thought of as engineering intelligent behavior. Right? So one question which we could have in the science of intelligence is a hypothesis that competition in sufficiently rich environments will lead to emergence of intelligent behavior. Right? So suppose my goal is I want to develop an agent with common sense. Now, I need to start somewhere, right? So, if you look at evolution, one explanation is in evolution, there were finite resources, agents competed with each other, and that led to where humans are today. So maybe if we want to create truly intelligent agents or artificial agents, we want to recapitulate evolution, or the essence of evolution being creating environments which are sufficiently rich, let agents compete, and that will lead to emergence. So, one example of this work is, having this ant and the spider fight with each other. So it's a zero-sum game. If you go beyond this parameter, the agent which goes beyond gets a negative reward. The other agent gets a positive reward, and it wins the game. Right? And what they were able to show was, by having these agents compete with each other, we can learn some interesting skills of moving around, but also using the legs to fight the other opponent. But maybe fighting is specific to the task that we are doing, but the skill of moving around is something definitely useful, which could be leveraged for different tasks. Right? So maybe I don't need to design a reward function specific to walking or turning around. I can just say compete, and I would get the behavior of walking. Right? So maybe much easier than doing this reward design. Another example that we saw, a couple of times in the course was, this, team of blue agents and red agents, which are again engaged in competitive play, which leads to emergence of this intelligent behavior of first getting the ramp in and then blocking the open pathway so that the pink team or the orange team cannot jump in. So I would say if my hypothesis is that the way to go to intelligence is to recapture evolution in some way, then these works would be the kind of research that you might do, right? You might create environments and showcase that you are able to learn interesting behavior which looks intelligent. But there are, many let's consider one more hypothesis, right? One more could be the generative models of very large amounts of data will learn representations which are apt for few short transfer learning, and maybe therefore generalize to new tasks which the agent is given. So maybe if I believe in this hypothesis, I could focus on just developing good generative models. Now, what are examples of such a research direction? Some of the more recent ones are GPT-3, DALL-E, and CLIP. Now, let's talk a bit about why would we care about models. So what are generative models? Models that generate data. For example, Gyan is a generative model, something that we discussed. And turns out everyone has a different perspective on why we would want generative models. And so there's a very clear-cut mathematical definition. The clear-cut mathematical definition is, if I input noise, can I output a data point which comes from the distribution that I'm trying to generate? Right? For example, if I input noise, can I generate natural images? Why noise? Because I want some distribution from which I can sample, right? So that noise could be, a uniform distribution, a Gaussian distribution, whatever. So maybe another way you can say it is a mapping from random variables to samples from material distribution. Now, why are generative models thought to be good? Right? One possibility is they can do a model reasoning. And for example, if I have a giraffe which is occluded, maybe it is behind a tree, maybe it is behind a table. If I can generate data, I can reason this is how the giraffe must look behind the obstacle. Another reason is counterfactual reasoning. Right? I can think of situations. For example, if I say, think about pink elephant flying a yellow kite. Right? You probably have no trouble maybe thinking of something like this. So we are able to imagine situations which we have never experienced and reason about them and leverage them in order to make decisions. So generative models allow us the capability to generate stuff. Another thing is future prediction. Right? Can I predict what's going to happen in the future? A lot of what we saw in model-based works, which were trying to generate future predictions, and how do we leverage future predictions to infer actions or do planning? Then, depending on whom you ask, someone might say, if I can predict future, that's all I need to know. That's the key to intelligence. Right? So that's, maybe an AI person's perspective. If you're talking to computer vision people, they might say, well, I love pretty pictures. This is what generative models do. But if you are a hardcore machine learning person, you might just say likelihood, because now I'm able to describe the data in few number of bits. And that is what I care about. Right? But there's some reason to believe why generative models are a good bet as a mechanism to develop intelligent agents. And so the most exciting results, I think, which came up recently was from this paper DALL-E, where they were showing some examples of counterfactual reasoning. And for example, we can put a text prompt. For example, illustration of a baby daikon radish in a tutu walking a dog. Right? And these are the images which get generated from the model. Right? So this model is trained on very large amounts of data, paired data between images and text. And the underlying model is a transformer model. Not going to go into the details. Another example is, armchair in the shape of an avocado. Presumably the model never saw such examples in the training set, but still it is able to generate such things. Right? Why is this exciting? Because these are some very concrete examples of the potential of doing counterfactual reasoning, right, by just building generative models. Another hypothesis. So, feel free to interrupt me. I think we have some fair amount of content to go through. But, if you want to interrupt me, stop me for a discussion, feel free to do it. So, another hypothesis, we can have is, for example, cooperation in multi-agent environments will lead to things like emergence of language, and then language would be the basis by which agents can collect a lot of information about the world, and then we can bootstrap intelligence on top of it. So let's consider multi-agent setups. Just some background, and then we'll see where we are in this language emergence stuff. So in a multi-agent setups, we might have multiple agents, agent 1, agent 2, agent 3 shown over here, and there's some landmarks which might serve as goals where agents might have to go. Now, if you look at a multi-agent setup, there are many choices which one needs to make. For example, the first choice is, are we solving a centralized problem? Which means that the actions of all agents are decided by some central place or a server that's aware of states of all the agents. Right? It's like, think of all nodes which communicate to a main node. The main node tells all the agents what to do. They end up doing that. Right? So that's centralized control. Or are we interested in decentralized control? So individual agents making their own decisions. Right? Now, in this case, each agent may or may not be aware of the state of the other agents. The distinction is who makes a decision. Is it some central entity making a decision? Or is it each agent making a decision on its own with what information it has? Right. So, for example, if tomorrow all the cars on the road became self-driving, and then we could probably have a centralized controller which decides what is the route every car should take, or what happens with airplanes today, right? Somewhere centrally we decide what is the route each airplane is going to take, and that is the route which airplanes take when they fly. But if all cars are not self-driving, some of them are human-driven, some of them are self-driving, the centralized system is not really going to work because I cannot feed in the data from the human car into the centralized system. Now each car has to make its own decisions. And so that would be more like decentralized control. Now, when we are trying to, learn how agents can maybe collaborate with each other to complete a task, the choice between centralized and decentralized control is not black and white. It can be gray. For example, the training could be centralized because we can assume access to some privileged information during training, but the deployment is decentralized. It's another place where we looked at privileged information was sim to real transfer. Right? We looked at how privileged information can help us train much faster in simulation or much more efficiently in simulation, and then transfer to the real world with where that information which helped us train faster is not available. Right? So similarly, in multi-agent setups, we could train in a centralized fashion, but deploy in a decentralized way. Then the setup could be cooperative, it could be competitive, or it could be both. Right? Where there are teams, so if we have two teams competing with each other, then within the team there is cooperation, but between teams there is competition. So, one perspective you might have is, well, if I just consider one agent, say agent one, then for this agent, the other agents are just part of the environment, right? So I can pretty much just ignore that the problem actually has multiple agents and just apply reinforcement learning as we have studied in the course. But turns out that this is challenging. Why is this? Because agents are continuously learning, which means that they're always changing. Right? Now, if they're always changing, this means that from perspective of one agent, if the other agents are part of the environment, and if these agents are always changing, it means the environment is non-stationary. That the environment is not the same. Like for example, if I take my hand forward to do a handshake, sometimes you bring your hand forward, but initially you don't bring your hand forward. But later on you start bringing your hand forward, right? So initially I might bring my hand forward, but because you don't bring it, I might stop doing it, right? So because the other agent is changing, the environment is no longer stationary, right? And that can create issues. But we have also looked at off-policy learning, right? Where we said, well, it doesn't really matter, right? My data can come from some other policy, such as in Q learning, and I can put them in my replay buffer and still learn from it. So one question. So maybe before I go into the question, is the setup clear? Are there any questions on why multi-agent can be challenging? Yes, clear. Okay. So what we saw in Q learning was, we can have some policy from which we collect data, which is different from the policy that we are learning, and we can put the data into a replay buffer. So can I still use Q learning over here, right? Suppose the Q function of the ith agent is QS, AI, where I refers to the action of the ith agent. And if I just use DDPG, would it just work fine? So we have a small poll again for this question. So let's go to that poll and see what people think. So the poll has two questions. It says no, because Q learning is off policy. And the second is yes. And so the first question is saying, is multi-agent learning a concern for Q learning? So you spend some time, look at these options, and mark your vote. So we'll take maybe 15 more seconds, and then we will discuss. So last 5. So if you're on the fence, now is the time to. That is weird that you don't get an option to poll. Did you not join through the MIT ID? I'm not sure.
I joined through the MIT ID. Yeah. It's weird. Like I get an option to end the poll. I can see results, but I can't really vote.
Oh no, that's sad. Was it the same case with previous polls or just this poll?
No, just this one. Like previous ones worked.
Okay, we'll debug it later. I think.
Oh,
remember your answer in your head for now. So let's look at what people think. People think that yes, non-stationarity in Q learning would still be a concern because experience in replay buffer is invalid because every agent's policy is changing. Right? So I think this is true. For the way The trick to making Q learning work was to include the action as part of the rewards, right? So if you look at value function, V of S, that does not have actions as input. Because the Q function depends on the action, we could leverage data from a different policy in a single agent setup. Now, how can we overcome non-stationarity in a multi-agent setup? The trick is very simple, right? We can just use actions of all the agents. So if I knew the actions of all the agents, then I would make Q learning harder because I'll run into data sparsity issues, but it will no longer be non-stationary. Right? So it's a similar idea to state augmentation that we discussed earlier. So this was the trick which was proposed in the paper called multi-agent DDPG. So they have this algorithm which they labeled as MA-DDPG. And over here, there is privileged information. The privileged information is the fact that I know the actions of all the agents, which means that my training has to be centralized. Right? So for example, if I have policies pi1 to pi(n) for n agents, I need to know what action each agent took. So the training is centralized because I need this privileged information, but my deployment is not centralized because I never need the Q function in deployment. I can just use my policy. Right. So we can just look at MA-DDPG algorithmically. It's the same thing. We start an episode. We have the initial state. Each agent would choose its action. You would add some noise. Each agent would execute these n actions. We would store the transition in the replay buffer. Then we end up sampling data from the replay buffer. My Q function depends on actions of all the agents. We minimize the critic loss, as we have discussed in the class. We minimize the actor loss, as you did in your homeworks. We have the target network update, and that's it. Right? So the technique that we discussed of how to overcome non-stationarity by state augmentation is used over here, and turns out MA-DDPG works better than DDPG in multi-agent settings. Now, multi-agent algorithms is a huge field in itself. Hopefully what we got an idea is what is the difference between multi-agent learning and single-agent learning. And we saw how we can construct at least one multi-agent algorithm. So now what I'll do is I'll talk about the problem of communication in multi-agents. And we won't really have time to talk about more multi-agent algorithms. Right? So let's think about communication as a problem, right? Or not as a problem, but if my agents are trying to cooperate with each other, one thing that you would maybe want the agents to do is to communicate, right? To say so that they can collaborate on the task. And one thing you can think about communication is just a part of your action space. And if you're speaking, it's just a part of your action space. You're moving some muscles at the end of the day, right? So, you can say the agent has some action space and how it moves, but it has some other actions, which could be a discrete, action space. I could have a fixed vocabulary of say n, and I could output one of those n symbols. Right? So for example, the C might become my communication symbol. But turns out, this learning to communicate is actually very hard. And so what we can do is we can give the agent the capability to communicate, but learning to communicate becomes quite hard. Now, why is this? Does anyone wants to take a guess on why learning to communicate is hard? No. Okay, so I'm, maybe because we won't have more lectures, so I will not wait for more responses. So the problem is called assignment. The problem is, suppose if I output a correct communication, but the other agent takes a wrong action. If I get the reward in the end, I don't know if my communication was incorrect or the action taken by the other agent was incorrect, which is a form of a credit assignment problem. And this really makes learning to communicate quite hard. So let's consider a multi-agent setup, and see what people have done in the communication land. We just walk through one very one example from one paper, right? So let's assume that we have n agents and each episode is of t time steps. My reward function is described as following. So my reward function is the sum of rewards of all the agents, and we want to find the policy pi. N is the number of agents, and M is the number of landmarks that we have. Let's assume the state space of each agent has the location of all the agents and the location of landmarks, right? So plus some properties of the landmark, which is X. Then C is the communication from all the agents. So this agent knows what all other agents are communicating to it. Then M is just some vector, which is internal state of the agent or memory of the agent, because it might want to remember the communication from past instances or past time steps. And G are the goals of the agent, and each goal might be specific to the agent, right? And let's assume there's a diverse set of goals, because if you just have a single goal, there is no need to communicate, right? You only need to communicate if there is diversity in what you're trying to do, and goals are kept private to each agent. And again, I'm going to re-emphasize that the reward function is shared across agents, in the sense that what we're trying to find is a policy pi which maximizes the sum of rewards. Right. So let's, for simplicity, assume that each agent has the same policy pi. Right. And we are trying to maximize the sum of rewards. So now I have one more poll for everyone, which is on this shared reward function. So I hope we can see the poll now. And the poll is asking about, is having this shared reward function a good idea or a bad idea? And if it is good or a bad idea, why is that the case? Right, so let's take, maybe 30 seconds to read the poll and then answer it. So 15 seconds to go. Okay, 5 more seconds. If you're on the fence, now is the time. Okay, so let's end the poll. See what people think. Pretty much everyone says that it creates a challenge because assigning credit to a particular agent is unclear. Right? So if I'm just maximizing sum of rewards, some agents are doing good, some agents are doing bad. If I sum everything, I don't know who is doing good, who is doing bad. So, okay, but why do people choose such reward functions? Because sometimes it is very natural to choose such reward functions. For example, if there's a team of soccer players, it's kind of hard to give a reward function for each player. That you might just say the overall goal is to score, right? And sometimes your training is centralized, so you just end up accumulating rewards of all the agents. Now I'm actually going to skip the details of this paper, but I'm going to just describe very briefly how things are working. So we have n agents and they have their end states. There's a communication from n agents, there's a memory which all of these agents have. Now, all of this constitute the observation O. Now, each agent has the same policy pi based on this observation, which is distinct, for each agent because the memory of each agent is different, right? We will end up, each agent will choose its own actions. They'll execute the action, and then we'll get the next state, right? So this is how the environment is going to roll forward. Let's look at how the policy network looks like. So the output is how the agent should move and the communication. So, and this policy network takes as input the communications, and these communications have you can think of this as a recurrent network where there is some memory. So I accumulate communication throughout the history, I pool them, I get some feature representation. Then there's a goal which the agent is trying to achieve, and there's a state of all the agents. So we concatenate all of this, and from this we're outputting the action and what the agent wants to communicate. So I'm using this work as a reference, which is emergence of grounded compositional language in multi-agent populations. And this particular work optimizes this policy by using a model-based method. So they end up having agents interact with each other, they learn a dynamics model, and then they optimize this policy through it. Again, details are in the paper, but we'll just skip to the results. And what they're showing over here is what kind of communication agents end up learning. Now, maybe the communication is, go to blue or go to green, which is saying what is the object I want the agent to go to. Over here, the large circles are agents, and the small circles are the landmarks where the agents need to go. So a couple of things to notice. Just notice how simple this environment is. It's pretty much a 2D world. And we are not even operating from vision. We are operating from a very low dimensional state space, which is the X, Y locations. Right. And one thing to be careful is that these, labels that they have put, go to and blue, are interpretations. Right. So they never defined what the vocabulary is. What they find is, if I have K words that I can say, when the agent says the ith word, it always seems to move towards a certain direction. So by observing, multiple rollouts of the policy, one can assign a semantic label to each of the words in my vocabulary. So the agent, seems to learn, these concepts of saying, go to this, go to blue, go to green, right? Or look at, in a particular direction and, go to a particular direction. Now, if, I want, as a scientist, I want to, think about the question, how did language emerge, right? So, this is, one way of studying, how can language emerge? And for example, I could say, these are the characteristics which natural language has, right? And I can list them down, and then I can ask the question, if there are two agents or, n agents which are trying to cooperate or compete with each other, is it possible just by that process, language can emerge? Now, what I will do is I will look at the language code which the agents are using during the rollouts and try to match if my natural language has the same properties as the codes which the agents are using. If both of them are similar, I have a very concrete hypothesis about how language could have emerged. So, that's what I wanted to say about, maybe a science. So when I say science of intelligence, right? These questions, so these questions, for example, how did language emerge, is maybe not directly or practically useful because we are not processing natural language. we're trying to understand how did language came into being. Similarly, the previous two questions were about how did intelligent behavior comes into being. Another hypothesis we might have is, instead of directly training for an end task, if an agent learns to do many things, it will not only transfer better, but also outperform single task models trained on the training task itself. Right? So for example, if I want to do image recognition, the typical paradigm right now is to train end-to-end to do image recognition. But maybe that's a bad idea. That maybe if I do a lot of other things, maybe I can learn something by doing those other things, which can help me be even better than training directly on image recognition. Now, why would I even pursue this hypothesis? Right? First, let's talk about some concrete evidence. Right? So if you look at the field of self-supervision, in which we are trying to learn features by some auxiliary tasks. Right? For example, trying to predict audio from video, trying to predict what is the color from a grayscale image, so on and so forth, what we discussed a couple of lectures before. And all this self-supervision has culminated into what we today call contrastive learning. And what we find is the performance of the latest and greatest contrastive learning methods are very close to the performance of supervised learning methods. So by doing something which is very different, right, by trying to say, is this image the same as this image, which is not an image classification task, we can learn features which can be quite close or which can match the performance of training directly for supervised learning. Similarly, maybe you can consider human learning, where infants seem to be doing a lot of different things. Right? They might keep pushing this object for a long time and then do a different thing, seemingly random things, but a lot of different things. And there is many developmental psychologists such as Alison Gopnik who believe that when kids are doing or they're solving these tasks, they're learning models of how the world works, or they're learning algorithms which teach them how to solve problems. And then they can leverage these algorithms of how to solve problems or the models that they have learned to solve new tasks that are presented to them. So we can take this as a hypothesis, right? And say, well, maybe we can get some inspiration from this, or this could be an rationale for why performing a lot of even seemingly random tasks could help us build intelligent systems. So we actually covered bits of this hypothesis in the course, right? For example, if I have to go with this hypothesis, the first question is what tasks should I be solving, right? And then if I solve these tasks, I need to condense this data into models of how things work. These models should be able to solve new problems, learn from few examples, require minimal supervision, work from raw observations. So in some ways, the experiments generate data. This data can be condensed into models of how things work. And then these models in turn can inform what experiments to run. It's something that we saw in curiosity-driven exploration and other intrinsic reward methods. But then there is too much to learn in the world, right? I mean, there are too many books to read. There is too much on the internet to read. So, agents have biases, but sometimes they also do things by observing their friends, or, as humans, we observe our friends, we observe other people doing things, and we learn from them, right? So imitation can, help bias this exploration, or it could help perform more complex things. And another question which comes up is, what is the initial state that we are starting from? So if we can put, these four things together, one could have this never-ending self-learning loop. We're running new experiments, condensing them into models. Models tell us what to do next. But because the scope of everything is too much, we can get biased. through agents or experts. Right? So, we concretely saw this, intrinsic reward-based methods to generate data. We looked at, some examples of how we can use data to build models of how things work. And they had, some of these properties, right? And this is, the loop that I just discussed previously, but also by connecting different parts of the material we covered in the course, we could form this loop, right? Then we also looked at, how models can help us imitate other agents, And then, we can ask a question, what are we building into our agents? Because we are building in some things, right? For example, we're building in the fact that we are building models which forecast the future. And, we could also build in more things by investigating human priors. So if, my hypothesis is that by solving a lot of different tasks, or even presumably self-generated tasks, we can develop an intelligent agent, maybe this is one framework that one could follow. So unfortunately, we don't have enough time to go through this engineering intelligent behavior. So, what I'll do is I'll just skip to the end and just give you a flavor of these questions. So one question, which you can ask in engineering intelligent behavior is, for example, can analytical controllers help learning-based methods or vice versa? It could be combined analytical methods and learning-based methods. Right? Other question we could ask is, for example, can we make use of task-specific constraints to aid learning? So if you think about these questions are, again, generic, but they are trying to solve some particular problems, right? They're trying to see if there are some specific constraints of a task, or maybe I know how to solve some sub-part of a task through classical control methods. How can I use learning? Right? So I would say this is more like engineering intelligent behavior, and we are not necessarily asking a broad scientific question. Hopefully this gave you some perspective of, the science of intelligence versus engineering intelligent behavior. I think when you're doing your research, it is very good to have this distinction in your mind. So with that, I'll close the lecture. One thing is that, there's this MIT course survey, which I highly encourage everyone to take. Some of you had this feedback that we should have recitations in the course. So, we couldn't do it this time, but maybe we can do it next time. But how does that get decided? If you go to the course survey and say, we really think recitations would be important, right? Then MIT would know it. It might, offer us more resources to make that possible. Right? But you might also have other kinds of feedback about the course, right? Of how it could change in the future, what things you like, what things should be a part, should not be a part. Just feel, I would highly encourage you to do this survey, which is MIT wide, instead of the surveys which we're doing in the course, which were specific to the course.